Some galaxy clusters are racing toward the same distant point. This motion is faster than most models predict. The immediate fact is simple: large-scale motion exists that challenges expectations. Picture thousands of galaxies drifting coherently across hundreds of millions of light years. That image shows why astronomers call this possible signal dark flow. It matters because such motion would break cosmological assumptions we rely on. The takeaway now is clear: something odd appears in large-scale galaxy motions. Imagine galaxy clusters like leaves drifting on a slow river. Dark flow names a coherent, large-scale motion of those clusters. This matters because standard cosmology predicts mostly random, peculiar velocities. Gravity from known structures should scramble, rather than align, those motions. The mechanism involves gravitational pulls slightly altering cluster velocities and photon scattering revealing those changes. For example, one analysis reported motion across about 800 million light-years. That measurement implied speeds of a few thousand kilometers per second, so the claim is surprising and it challenges our cosmic assumptions. Astronomers detect tiny motion using microwaves scattered by hot gas. The process is the kinematic Sunyaev-Zel'dovich effect, a small Doppler imprint. It matters because the effect links cluster velocity to microwave temperature shifts. The mechanism works when cluster electrons scatter photons, shifting their frequency slightly and creating microtemperature differences. Observers stack signals from many clusters to lift the tiny imprint out of noise. For example, early WMAP analyses stacked hundreds of clusters and reported a coherent dipole. Measurement difficulty is high because shifts are about 1 part in 10,000. So the method is clever and also technically fragile. A conservative explanation is local massive structures tugging clusters. Nearby superclusters can bias inferred bulk flows and mimic coherence. This matters because known mass avoids rewriting cosmology. The mechanism is simple gravitational attraction altering peculiar velocities and projection effects amplifying apparent directions. For example, the Shapley concentration exerts measurable pull on local galaxies. Simulations also show rare, large bulk flows can appear by chance in limited samples. So misestimated mass or statistical fluke could produce an apparent dark flow. Net result: local causes remain plausible and must be excluded first. If local pulls fail, the implications become extraordinary. Something beyond our horizon could gravitationally tug visible matter. This matters deeply because it would violate assumed large-scale uniformity. The mechanism could be a massive overdensity outside our observable patch, creating a long-range pull. Another mechanism imagines a collision with another bubble universe, imprinting a bulk velocity. For example, estimates place the required mass at millions of galaxies equivalent. Such ideas are speculative and require extreme evidence to accept, so non-local explanations are dramatic but remain remote possibilities. Different experiments reached different conclusions about dark flow. WMAP initially reported a coherent signal, and excitement followed. Later, Planck's team found no significant detection, and controversy grew. This matters because reproducibility is key in cosmology. The mechanism of disagreement often lies in filtering choices, sample selection, and instrument noise. Independent reanalyses sometimes find weaker flows or none at all. For example, Planck's higher resolution and different pipelines reduced the claimed signal. So the current picture is messy, and skepticism remains appropriate. A confirmed dark flow would force broad cosmological revisions. The cosmological principle assumes no preferred direction on large scales. That assumption underpins many dark energy and density measurements. The mechanism of change would alter inferred expansion parameters and affect galaxy formation models. For example, measured cosmological parameters might shift slightly if a bulk velocity exists. Such a discovery would ripple across theoretical astrophysics and cosmology. Bottom line, a real dark flow would reshape how we model the universe. Upcoming surveys will test dark flow with far greater precision. eROSITA will catalog many thousands of X-ray clusters, boosting samples dramatically. Euclid and LSST will map galaxy positions across huge volumes and measure subtle motions. Improved KSZ campaigns will aim for direct peculiar velocity detections, reducing stacking reliance. For example, combined probes could reduce errors by factors of several compared to earlier analyses. The mechanism is straightforward. More data reduces noise, and cross-validation exposes systematics. So future instruments offer a realistic path to confirm or refute dark flow. We still see hints of a vast, unexplained drift toward something unknown. If you want updates, follow for future discoveries.